Have you ever just looked at a microchip and wondered what's really going on in there? I mean, we see these pictures of incredibly complex patterns, but how does a designer get from just an idea to this tiny functioning city with billions of transistors? Well, it's not as chaotic as it looks. Actually, it's super organized, all thanks to a system that, you're gonna love this, works a lot like a kid's toy.
So yeah, how are these things really built? Do engineers sit there and draw every single transistor by hand? No way. That would be impossible. Instead, they use this brilliant system of pre-designed, pre-tested parts that just snap together. And honestly, the best way to get your head around it is with an analogy we all know and love. And that analogy, which even the pros in the field will tell you is spot on, is Legos. Seriously. Imagine you're building some massive, complex spaceship model. You wouldn't start by melting down plastic to make your own bricks, right? Of course not. You'd use a box of standard, perfectly made Lego pieces. Chip design works almost exactly like that.
So that big box of digital Lego bricks, in the industry, it's called a standard cell library. And this is the fundamental toolkit that pretty much every modern chip designer on the planet uses to bring their designs to life.
Okay, so what is it formally? A standard cell library is basically a collection of logic gates. These are your tiny little decision-making circuits, things like AND gates, OR gates, inverters. Think of them as your classic 2x2 red brick or your 2x4 blue brick. Each one has a very simple, very specific job, and they've all been designed and tested like crazy to make sure they're perfect.
And just like real Legos, these digital bricks have to follow some incredibly strict rules. They're designed to fit into these perfectly neat rows. Why? Well, because every single cell has to have the exact same height. Their power and ground lines are always in the same place, and all their connection points are laid out on a super precise grid. This is what makes the whole system work. It guarantees that any piece can connect to any other piece, just flawlessly.
Okay, so if you have this amazing box of digital Legos, how do you tell your design software which specific box you want to use? Well, you've got to point it to the right instruction manual.
In the chip design world, it often comes down to a simple command, something like read libs. This basically tells the main design tool, hey, for this project, these are the Lego boxes you're allowed to play with. And the files that it points to, well, they can look a little cryptic.
For example, you might see a file name that looks like this, tt1v5c.lib. I know at first glance that looks like complete and utter nonsense. But it's actually a secret code, and it's incredibly descriptive once you know how to read it. Let's crack this code together. The TT stands for typical. That just means the transistors in these cells are expected to perform under totally normal manufacturing conditions. 1V means this whole library has been tested and characterized to run at a 1-volt power supply. And 25C means it's all designed for a normal room temperature of 25 degrees Celsius. So all of a sudden, that gibberish file name tells you the exact operating conditions these Lego bricks were built for. Pretty cool, right? All right, now that we know how to pick our library, let's pop the lid off this box and take a look at the different kinds of bricks we get to play with.
First up, you've got your basic workhorses, the combinational logic cells. These are the bricks that do all the thinking, all the calculations, in real time, with no memory. This includes your simple stuff like NAND and NOR gates, the absolute fundamental building blocks of everything. But you also get more complex pieces like an AND or invert cell, or AOI, which can do a couple of logic steps all in one go. You'll notice, though, that they're usually limited to about 4 inputs. Any more than that, and they just get too slow and power-hungry.
Now this is where it gets really interesting. Each of these cells doesn't just come in one flavor. Oh no, it comes in different drive strengths. Think of it like choosing an engine for a car. The X1 version is like your small, fuel-efficient engine. It uses less power, takes up less space, but it's a little slower. But what if you need to send a signal a really long way across the chip or power a bunch of other gates? Then you need the X2 version, a bigger, more powerful engine that's way faster. But you guessed it, uses more power and takes up more space. It's a constant trade-off, a balancing act between speed, power, and size.
So, we have bricks for calculating things, but what about remembering things? A chip has to be able to hold on to data, right? That's where sequential cells come in. These are the memory bricks, and the most common one is called a flip-flop. Its one and only job is to hold on to a single bit of information, a 1 or a 0, and not let go until the clock tells it to. And man, the library gives you a dizzying variety of these memory bricks. I mean, it's wild. A designer can pick one that grabs data exactly when the chip's clock signal rises, or one that acts when it falls.
They can get a flip-flop with a reset button and even choose if that reset should happen instantly or wait for the next clock tick. The library has dozens of these pre-built combinations, which lets the automated tools pick the absolute most perfect, most efficient one for every single bit of memory on the entire chip.
But a chip isn't just about logic and memory. You also need bricks for the actual structure, these specialty cells that make sure the whole thing is physically sound and electrically stable.
These are the helper cells. They don't do any thinking, but the chip would totally fail without them. You've got filler cells, which are basically just blank Lego pieces to fill in any gaps in the rows for manufacturing. You need tap cells to connect the silicon base to the power lines to prevent all sorts of nasty electrical problems. End caps give you a nice clean termination at the end of each row, and decap cells, they act like tiny shock absorbers for the power supply, smoothing out any dips or spikes in voltage.
Now for my favorite part. What if you've built your entire Lego masterpiece? You're just about to put it in the display case, and you find a mistake right at the end. You do not want to tear the whole thing down. Well, for that, chip designers have a secret weapon: engineering change order cells. We just call them ECO cells. A friend of mine who designs chips saw a really clumsily patched water pipe once and just pointed and said, "Hey, that's an ECO. It's a late-stage fix. It might not look pretty, but it absolutely gets the job done." When you find a bug just before, or sometimes even after, the chip has been made.
The idea is actually pretty genius. You strategically sprinkle a bunch of unused spare gates throughout your design. They just sit there, not connected to anything, doing nothing. But if a bug is found late in the game, instead of starting all over, you can perform microsurgery on the chip itself. You cut a few of the tiny metal wires and reroute the signals through one of these spare gates to fix the logic. It's a clever hack that can literally save millions of dollars and months of work.
So we have all these different Lego bricks. But think about it for a second. Does the tool that's just trying to arrange them in neat rows really need to know about the complex physics of the transistors inside each brick? Absolutely not. And this brings us to the final and maybe the most important concept of all: abstraction.
Abstraction is the art of strategic simplification. The library gives different blueprints, or views, of the very same cell for different stages of the design process. Each tool gets only the information it needs to do its job and nothing more. This makes the whole process incredibly fast and efficient. And it also protects the secret sauce, the valuable intellectual property of how each little cell is actually built.
Okay, let's follow one cell through the process. The timing tool. Its only job is to ask, how fast are you and how much power do you use? It gets a simple .lib file with just that info. Then there's the place and route tool. It's like the architect arranging the bricks. It only needs to see the physical outline, the block's shape and where the pins are. It gets a .lef file. It could not care less what's inside. It's not until the very end, when the chip is about to be manufactured, that the full, top-secret blueprint, the .gds file, is finally revealed.
So, when you put it all together, you realize that the standard cell library isn't just a box of parts. It's this highly sophisticated, deeply intelligent system. It's a collection of pre-tested, standardized, and abstracted building blocks, complete with all these different blueprints for every single piece. It's the system that allows a handful of humans to manage the mind-boggling complexity of building a city with billions and billions of transistors.
And that leaves us with one last big thought, doesn't it? This whole incredible system is built on layers of abstraction and trust. Trust that the timing models are right, that the physical outlines are accurate, and that the hidden guts of the cell are flawless. So the real question is, in a world that's built on these simplified views, how do you really know that your fundamental Lego bricks are truly perfect?